Thank you. So in 2002, when I graduated, machine learning was sort of just an academic discipline. It was occasionally used here and there in industry. And now, a decade later, that's changed dramatically. So in particular, it's easy to credit tens of billions of dollars in revenue per year to machine learning in one sort or another. So I'm going to tell you a little bit about this, and then and a little bit about what I've done to help make this true. Okay, so when you go and you look at a modern machine, and you look at the state of its RAM, you discover that the RAM in a machine doesn't just have compiled code. A good portion of what's used in the RAM is essentially data-derived code, or data-derived stuff that's used to make the system run. So machine learning you can think of as using data to predict useful things. And then some portion of the code is, of course, compiled. In many systems, this is still the majority. But in other systems, data code which is essentially derived directly from data is what's there. This is a real change in the way that computers run, and it's created a lot of opportunities of one sort or another. Okay, so let me give you some examples. So search engine results are machine learning to a significant extent. There's still a large human element in terms of how you set the system up, but a lot of it is also data derived. Another example is Connect. Connect has this kind of RGB D is depth camera, and from this signal you can derive the pose of humans, even with various occlusions. That's machine learning in action. Spam prediction is the example you can tell everybody. So when emails come in, maybe if the word Viagra means it's spam, but you know, occasionally it's not true because you're a doctor and you're actually talking about Viagra, or maybe it was actually Cialis in the email, and so you start to think about this. It becomes very difficult to create a program to detect spam unless you're using the data that's actually there to help create the program. Another example is automated arbitraging. So this is what high-frequency traders are doing. This is some good bit of machine learning which is used in this kind of situation. There's a lot of headhunters which pester you if you work on machine learning. I have a friend, by the way, that is in machine learning at Princeton. He has a program that's keep kids off the street. Oh, and I also have another friend that is working in political campaigns, trying to figure out the most efficient way to persuade people to vote for one candidate or the other. Okay, so these are examples of machine learning, just to give you a sense of where it gets applied. There's kind of two types of machine learning, which you're starting to see. There's kind of the older type, which was studied in the 1990s and which is routinely used today. And then there's a newer type which is developing, which we'll discuss next. So the older type is called classical supervised machine learning. In supervised machine learning, what happens is you pick some problem where programming fails due to case complexity. So think about the spam example. You know, maybe an email with Viagra in it is spam, or maybe not. Maybe there's an exception. But then, you know, I'm sure doctors get spam too, so there's an exception to the exception. And you start getting this really confusing, I can't figure out how to really distinguish things because there's a whole bunch of cases situation. And when you run into these kinds of situations, you start thinking about machine learning. Okay, so that's one thing. You want to have a problem where the conventional programming approaches fail because of this kind of case complexity. And then the other thing that you want is to have data. And the traditional way to get this in classical supervised learning is you hire people to label emails as spam or not spam, right? Okay, so you have some input, which is the email, and then you have some output, which is the label. This is spam or this is not spam. You gather a bunch of these emails, you shove these into a learning algorithm. The learning algorithm outputs a function, which is then used to solve this problem in the future, to predict whether an email is spam or not. Okay, so this is the classical approach. The internet has created enormous data sets, and when you have all this data around and you're a machine learning person, you're like, oh, what can I do, right? Because these are not explicitly labeled. Nobody pays somebody to click on something, right? To click on an email or to click on a web result or to click on an ad or various possibilities. So you want to create a new paradigm for doing machine learning. So there's sort of the light version of this paradigm, which is when you're still doing classical supervised learning almost, but now you're taking advantage of the ability to quickly hire people to be editors. So Mechanical Turk is sort of the canonical system, but there are others for quickly describing a task to people and asking them to solve it. So you use Mechanical Turk to get a labeled data set just as before, but now there's an extra element, which is that the learning algorithm can start choosing which examples to feed into Mechanical Turk to get labels. And because the learning algorithm is controlling its own input, you can get into a feedback loop where things go crazy. Or you can get into a feedback loop where things are a factor of 10 more efficient. And when you're paying for labels, a factor of 10 more efficient really matters. The other thing, which is even more exciting, is when you have these computer-mediated transactions of one sort or another. So somebody comes to a website, and that website wants to display a news story, display an ad to make some money, and then maybe display some other content as well. And the question is, what content do you actually provide? Right? So the thing which is tricky here is that you only get feedback about the things you actually display. So in classical supervised learning, you know, this was the right choice, and that was the wrong choice, and that was the wrong choice, and that was the wrong choice. In interactive machine learning of this sort, all that you do is you get feedback about one of the choices. And that makes a big difference in terms of what kinds of techniques you can apply, and also in terms of these feedback loops, which can start to be very fun and exciting. So in general, what's happening with these interactive machine learning systems is that you have much more data, and you have a much more tenuous connection between the data and the solution. So teasing out exactly how to predict things is the challenge for these problems. You have vastly more data, and that's a great leverage. Okay, I'm going to tell you a couple of projects. One of them is Vowpal Wabbit, and this is an experiment in trying to scale up learning algorithms. VW is perhaps 2 orders of magnitude more scalable than any other public system which is available. So there was an ad prediction data set that we were playing around with. It was about 20 terabytes. Tera, by the way, is a great word because, you know, mega, giga, tera, they're all the same length. So you think of them as sort of the same, but tera is like terror, right? So yeah, so it's like hide the kids, the data's coming through. So you have a 20 terabyte data set, and you have about 17 billion examples of input and output. You want to learn a predictor with 16 million parameters. I'm telling you something about the state of the machine which is going to run the learned predictor. So we had a cluster of 1,000 machines. We could train a very high-quality predictor in about an hour with this. So this is open source. This is available for use. VW gets used by a number of companies. One of the smaller uses, but one of the funner ones, is eHarmony, where, in fact, VW is used to find true love. Okay, so that's kind of scaling up. For interactive machine learning, you need to deal with significant scales of data because you just have much more efficient methods for gathering data. The other thing you need to start dealing with is these interactive loops of one sort or another. And last year, when Craig Venter was speaking about personalized medicine, I said we worked out the mathematics of personalized medicine. It turns out that this is the same problem, is trying to figure out which ad you should display or which news story you should display. Because in each case, for the patient getting treated, you're only going to get feedback about the treatment, right? And so you have a problem with the same structure. So I can give you methods for doing personalized medical trials, which in effect let you do 1 million trials for the price of 10. Okay, so this general setting has a lot of applications just because of the way the world works. The way the world works is you're always going forward in time. There's no going back. You're in a situation, you make a decision, you see the outcome, and now you're under a new situation. Right, so anyway, fun stuff. Okay, so now for the business people, I wanted to discuss how you do machine learning. So the first thing that you need to do is you need to have an eye for what a machine learning problem is. And I've tried to describe this, think about this kind of case complexity problem. There's some problems which are kind of canonical, like machine translation or object detection or speech recognition. These are very canonical ones. But there are many other possible machine learning problems. Once you start to get an eye for these things, you can see them coming up. You also need data. If you don't have data or you don't have a way to get data, then you're out of luck. You're stuck. And then you need to hire a data scientist. Data scientist is a new profession which has been coming out. This didn't exist a decade ago. So data scientists are the people who take the data and try to figure out how to make it do something useful. And then it takes time. And the amount of time can vary greatly. It can vary with the problem. It can vary with the quality of the person. The quality of the person could make a difference between a week, a month, or never. And the harder the problem, of course, the more you really want the good people. And then another thing which is very common to these problems is that if you really care about the problem, you're going to get a solution, and that solution is going to kind of work. Maybe it'll work good enough, or maybe not quite good enough. But you should expect to want to refine these things indefinitely. When you think about a modern search engine, you should think about a system which has been continuously refined over and over and over again, each time trying to make things just a little bit better. That's the way these kinds of structures work. Okay, so now, this is the last thing. The question is, what's next? So it was very interesting to see, because when I was creating these slides, I didn't know the topic that we were going to be discussing was education, and then medicine for some of the other Siebel scholars. So medicine is, I think, extremely right, because you have a combination of two things. You have a massively inefficient system, and this inefficient system is just not optimized to provide good health care. Doctors have all kinds of misincentives to overprescribe treatments or measurements of various sorts. Okay, so you have massive inefficiency, and then you also have data which is getting collected in a systematic fashion. Well, not quite yet, but they're starting to create data sets in a systematic fashion at various hospitals, and this is what the public health records, or the electronic health records program is about. So the combination of the data and the massive inefficiency suggests to me that there's a huge opportunity for machine learning to do interesting things. The other thing is education. So this is, I think, a little bit further out. But we're starting to see these massive online courses. And this is a very cool thing. It's quite possible that in the future, this will be the way we learn, because you can have a class which is optimized by 100 people and then taught to 100 million people. And it can be completely personalized and interactive, and we're just so far from there. If you take a look at what happens with the massive online courses, like the ones that happen at Stanford, the dropout rate was 75%, 85%. I mean, in a normal class, that would be catastrophic, because they just have so much scale. They're still like, yes, we succeeded. But you need to get that dropout rate down to 2%, right? And then, of course, eventually, many of us working on machine learning aim for artificial intelligence, but there's something to be done there. So that's a ways off. Yeah. Any questions?
Just in practical terms. Hi.
Just a moment. You go ahead. Go ahead.
Just in practical terms for us business people, the part of what's hard is not understanding this space is I have an interesting analytical problem. I don't know what class the solution applies to it, and I don't know who to reach out to find the high-quality data scientist, right? So there's a piece missing for my naivety in the process. How do you suggest people, if they think they have an interesting problem, approach that and better leverage this community to find the right person?
There are a number of SQL scholars that are machine learning people. Just talk to them. Describe the problem to them. They will be able to diagnose it as a machine learning problem or not, and they can either solve it for you or they can point you towards other people who can hopefully help solve it for you. Yeah?
Thank you for a great talk. SQL Scholar Class of 2013 from UFI, Computer Science. You talked about using machine learning for medicine, and there was a case study, a paper I read just recently, which says that support vector machines could be they are susceptible to noise in the data, and they have security threats such that if somebody from outside gives in some wrong information, that might lead to a wrong result. And if you talk of such things being used in medicine, how do you deal with such security measures being dealt with?
So the question is, what happens when the data that you're getting is fed to you adversarially, right? So when data is fed to you adversarially, things get a little more difficult. You need to create learning algorithms which are more robust to adversarial noise. And then there's several kinds of adversarial noise. I can give you the flip answer, which is you should use VW, because we've optimized it to deal with adversarial noise. It was designed actually to be a spam filter when it started out. So that's just the flip answer, though, because in many situations, you need to think about these things quite carefully, right? And you need to examine the problem carefully to think about what kinds of disturbances to the data you're getting. In medicine, I would imagine that it's not that bad adversarially, actually, because it's not like you have somebody who's actively trying to do click fraud or actively trying to defeat the system. I would expect it's more like negligence that you need to worry about, like somebody doesn't record something that they should have recorded, or somebody misrecords something that they should have recorded. And so when you have these kinds of situations, generally redundancy starts to become very helpful. And then another technique that I've seen be very helpful is when you kind of create simultaneously the global system and also a personalized system for each individual person or patient. So when you do that, if somebody is screwing with the system, then the complexity, the way the global predictor changes is it delegates all the screwing around to the local predictor, and that just doesn't carry over to the global predictor. Right? Yeah?
Elijah Mayfield, Carnegie Mellon class of 2011. I work in machine learning, both in medicine and health education. And on a daily basis, I'm working with both doctors and teachers. And the question I want to ask is about trust. So one of the big issues with machine learning in both of those fields is this sort of view that magicians work in machine learning, where you pass them your data, there's a black box, and then they come back with answers for you. What I have as a question for you is, how do you incorporate the opinions of doctors and teachers, the knowledge that they get from their own research, into the machine learning field? We get this in the ICML community with people like Machine Learning That Matters, the paper that came out. Mm-hmm. How do you get people to understand the effects of different choices that you might make within machine learning and make it not as much of a black box and get them involved?
So in general, the black box issue is pretty significant because the best systems are almost always the ones you can't understand. One trick that I've seen used is nearest neighbor, actually. So nearest neighbor is not necessarily the best approach to solving a particular problem, but you can tune nearest neighbor to be as flexible as a linear predictor because you can tune the metric which is used. And then when you're actually presenting the results, you can just present the individual cases. So for a doctor, this could be a very effective approach because a lot of their reasoning is sort of this kind of ad hoc, like, oh yeah, I remember this case from 13 years ago when this guy came in with symptoms just like this, right? So if you give people the case records that you're using to make the prediction, I think that is a pretty good way of disambiguating things. The other thing that I've seen be helpful is um, you don't necessarily so comfort with a black box takes time. So you just put the black box out there, and you make it a resource which is available to the doctor, and the doctor can use it and start to become comfortable with it making good decisions. This is the same way it works in your real life. Like, you don't actually understand how a TV works or how a car works, probably. These are black boxes in your life regularly, or a computer, right? Even that's kind of mysterious at times. So once you get used to their input and output characteristics, and you're familiar with them actually doing something pretty reasonable, then good things happen. And the last thing you asked about was how do we incorporate the expertise of people? That's in general a delicate thing, and you need to talk to the doctors about what matters in their opinion. You need to make that available to the learning algorithm so it can actually learn from these things. The other thing, which is I think very important, is that you really want to try to stretch for scale, because when you get a lot of data, you can start to separate out the signal from the noise in a manner which is just not possible with relatively small amounts of data.
John, thank you so much.
Thank you.
John Langford.